Okay. I think we can start. So, good evening, everyone. My name is Stanley Pocar. I'm the current president of the SEG UCE FIGEMPA student chapter here in Ecuador. It is a pleasure to welcome you all to this lecture. Our distinguished speaker today, Professor Richard Goldfarb, is one of the leading figures in the study of ore deposits and metallogeny. He holds a bachelor's in geology from Bucknell University, a master's in hydrogeology from the University of Nevada McKay School of Mines, and a PhD from the University of Colorado. Professor Goldfarb dedicated 36 years of his career as a research geologist at the United States Geological Survey, focusing on global metallogeny, orogenic gold deposits, and geochemical application in orogenesis. His remarkable contributions to the field have been recognized with numerous prestigious awards, including the SEG Silver Medal in 2011 and the SEG Gold Medal in 2023. Currently, he serves as a research professor at China University of Geoscience in Beijing, at the Colorado School of Mines, while also working as an independent consultant in exploration and mining. Thank you, Professor Richard Goldfarb, for this lecture. To the attendants, if you have any questions during the presentation, please leave them in the chat and we will address them at the end. Without further ado, we can start.
Okay, thank you very much, and I appreciate the SEG students inviting me to speak to you. Being an SEG is one of the best things you can do, and I think many of you students realize that. So thank you for having me. This is my email here on the opening slide. If there is any questions we don't get to today, feel free always to email me, and I am always very good at answering emails. Today I'm going to talk about orogenic gold, its geology, exploring for it, its genesis, what we understand, some things we don't understand or that may be confusing. When we talk about orogenic gold, we're basically talking about gold in metamorphic rocks. And I'll also contrast that a little with gold you're more familiar with in Ecuador, which are the more porphyry epithermal systems, which are more associated with magmatism in unmetamorphosed terrains. In simple thinking, this is an old slide, but it really shows well that there are really two ways to form gold deposits on our planet. You can take a granite and place it at shallow levels, generally in the upper 5, 4, 3 kilometers of the crust. That granite is a local heat source. It can release fluid and or help circulate surface fluid above it. And that magmatic and or meteoric water can form gold-bearing porphyries just above the top of the granite. If there's carbonate nearby, you can have gold-bearing skarns. And at shallow levels in the upper 1, 2 kilometers above those intrusions, you can form your low and high sulfidation epithermal deposits. So you're looking at a magmatic plus or minus meteoric water forming the gold deposits. The heat source is magma, and these deposits form in the upper 3 kilometers of the crust. The deepest gold deposits that are magmatic generally are just at 3 kilometers, your gold-bearing porphyries. If you have copper porphyries, they can be a little deeper, but these kind of gold deposits form from mainly magmatic water in the upper 3 kilometers. The other way to form gold deposits is when you bury rocks, you metamorphose rocks. When you change a shale and a sandstone to a greywacke and a schist, 3 to 4 volume% of that rock changes the fluid. That fluid carries gold down pressure gradients, which essentially could be horizontal, into large fault zones because there's lower pressure or you have a large fault. Those fluids get concentrated in the fault. There are earthquake events. They may move up 500 meters or a kilometer and form your orogenic gold deposits. So in this case, the fluid is metamorphic. The heat source is the geothermal gradient. And these deposits, depending on the gradient, can form as shallow as 3 kilometers or as deep as 15 to 20 kilometers. So these are really the two ways we form gold on our planet. When we explore for gold, and for this slide, we're going to ignore Witwatersrand, this great paleoplacer in South Africa that's produced a third of the gold on our planet. But ignoring the Witwatersrand and looking at global gold endowment, what's been produced and present-day resources, about half the gold we explore for is orogenic, or gold in metamorphic rocks, and half is intrusion-related, your porphyry, epithermal, and lesser skarn. Carlin deposits are important, but only in Nevada, USA. They talk about them in China, but they're not really present in China. Those are orogenic deposits. That's a mistake in the literature. So we're really, when we explore for gold, we look in metamorphic rocks for orogenic gold, or in our oceanic or continental rocks for intrusion-related gold. And once we started learning a lot about plate tectonics in the 1980s, that's when we developed our modern models of gold formation. We realized if we have oceanic arcs that eventually get accreted to continental margins when we subduct and we accrete, or if we have continental arcs like in the Andes, at shallow levels, we can form our epithermal and porphyry deposits with gold in the upper 3 kilometers. In contrast, as we add new material to a continent, we often add this as terrains accreting onto the edge of a continent. Those terrains often have large faults, sutures between terrains, and along those sutures we form our orogenic gold that may develop anywhere from 3 to 15 kilometers. And you can see with any amount of erosion, the intrusion-related deposits are quickly lost from the geologic record. But the orogenic gold deposits, because they form deeper, are better preserved back through geologic time. Much of our planet, especially our craton areas, expose rocks that were at 5 or 10 kilometers. And those rocks are now at the Earth's surface. So we've lost our intrusion-related deposits, but we've preserved our orogenic gold deposits, and that's why they have a broader distribution in space and time than other types of gold deposits. So when we look at the intrusion-related deposits, we see they're located in two places on our planet. They're located along the Circum-Pacific arcs and in the Tethyan arc from southern Europe down to Yunnan and Tibet, China. They can be in continental arcs, such as here in the Andes, oceanic arcs, such as here in the Southwest Pacific, but the key is young arcs, because these are the young magmatic systems on our planet, and these deposits had formed at shallow levels. You look elsewhere, such as in Brazil, or much of Australia, almost all of Africa, those are rocks that are much deeper. They expose rocks that were 5 and 10 kilometers. So we've lost the magmatic deposits from these areas, and the only deposits left are our orogenic gold deposits. If we look at the distribution of orogenic gold deposits on our planet, you could see they're all over the planet and of all sorts of ages. The youngest orogenic deposits are Tertiary and Mesozoic. They go from Nome, Alaska, here in North America, down to the eastern Cordillera of Colombia, where you have the Segovia Gold Belt. They also go from eastern Russia down to the South Island of New Zealand. We can look at Paleozoic orogenic gold deposits. The great belts of Central Asia are Paleozoic. The eastern Cordillera of Peru are Paleozoic. We can look at Neoproterozoic orogenic gold deposits that we often see here in Africa, in the Arabian-Nubian Shield. We can look at the Paleoproterozoic of North Australia, here in Homestake, in the middle of North America, which is right here, Or we can look at the great Paleoproterozoic gold fields of Western Africa, which some have rifted away with South America when it broke across, and now are on the north side of the Guiana Shield. And we can look at the late Archean, whether it's central Canada, whether it's Brazil, whether it's much of Africa, India, and Western Australia. We have our Archean orogenic gold deposits. So they can be all sorts of ages where we've preserved those rocks that were at 5 and 10 and 15 kilometers back through geologic time. Also, when we look at the time distribution, when you look at overall gold endowment on our planet, the intrusion-related gold and the orogenic gold are roughly equal. However, look at the distribution in time. Most of the intrusion-related deposits are tertiary or late Mesozoic in age. In contrast, an equal endowment of gold is spread in orogenic gold, but you can see it's spread over 3 billion years of Earth's history. So we have differences in spatial and temporal distribution of orogenic gold from other gold deposit types. And basically, orogenic gold is gold in metamorphic rocks. And it can be in the Archean cratons, it can be in the Phanerozoic accretionary origins, it can be high grade. More recently, we're mining very low grade deposits. This is the largest gold deposit in Brazil. It's an orogenic gold deposit called Morro de Ouro, or Paracatu. They are mining 20 million ounces of gold at 400 ppb. When I started, that was a distal geochemical anomaly, and now that's the biggest gold deposit in Brazil. The orogenic gold deposits form in rocks after they've been added to continents, deformed, and metamorphosed. But the new material added to continents has changed over geologic time as we change plate tectonics or tectonics over geologic time. On our hotter early Earth, plume tectonics were important, and we rifted the early continents, and we had volcanic rocks going into those rifts, then closing again, and that's why many of our cratons are dominated by greenstones, metavolcanic rocks. Beginning about 1.7, 1.6 billion years ago, the Earth was cooling, and rather than just collisions between Archean blocks, we were able to start subducting plates. And so rather than rifting and breaking apart continents, we started subducting and adding metasedimentary terrains to the edges of continents. So we had a lot more new material added to the continent, so it was sedimentary rather than volcanic. So if you look at orogenic gold deposits, and this confused people up to the mid-1980s, the older orogenic gold deposits are mainly in volcanic terrains or greenstones. The younger deposits are mostly in metasedimentary terrains, such as the Eastern Cordillera of Peru. But the deposits are the same. They form in similar manners, but just the dominant rock types have changed over time. And you may say, well, these grow along the edge of continents in later times since 1.6 billion. But for example, we can look at the great deposits of Central Asia, which you see here, the Paleozoic deposits, late Neoproterozoic deposits on the edge of Siberia and all through Central Asia. These are now in the middle of continents. But when you look at older orogenic gold, you have to look at what the geography looked like at the time the deposits formed. 600 million years ago or 500 million years ago, this is what the Earth looked like. So these deposits were forming on the edge of continents, though now they're in interior of continents. Similar, the Eastern Cordillera of Peru is inland of much of the Andes. But when those deposits formed in the Paleozoic in Peru, they were on the edge of Gondwana, and so along a continental margin. So plate reconstruction is very important to understand orogenic gold. Orogenic gold, intrusion-related deposits are associated with intrusions. Orogenic gold deposits are associated with large fault systems. In the Archean, such as Western Australia, we have this Boulder-Lefroy fault here, which goes for hundreds of kilometers in Western Australia and includes the Golden Mile, the world's largest Archean orogenic gold deposit east of Perth. We can look at Paleoproterozoic Western Australia, where we have closed sedimentary basins against volcanic rocks, and we have these large shear zones, large faults, and that's where the deposits sit. I worked for many years in the young deposits of Alaska. We have a large fault here, which is a terrain boundary. Some deposits sit here behind the town of Juneau, built on mine tailings. Others are on the other side of this fault. You can see the old pit out here in the rainforest. Basically, you need large structures, large river channels in the crust to focus fluid. If you're going to form a large orogenic gold deposit, you have to get a lot of fluid into one place, and you need big structures. If you don't have large structures, you're not going to have a large orogenic gold deposit. Along those structures, fluids are going to flow where you have open spaces. This is, again, Western Australia. This large fault strikes 155 to 165 degrees. Wherever there's a change in strike of 15, 20 degrees, such as here where that large Golden Mile is, you get second and third order structures, whether they're fault systems or second and third order shears between units, and that's where the gold deposits are located. So you want to look for changes in strike along major structures, because that's going to focus the fluid that's coming into the structures into favorable traps. Similar example, this is the largest gold deposit in Europe. It's an orogenic gold deposit, the Kitla mine here in Finland, where I've been working the last 6-7 years in this part of Finland. And you can see it's located where there's a 20-degree bend in this major structure. So you want to explore, you want to look at maps, you want to look where there's going to be bends in structure. And then you look at your second and third order structures along these, whether shears between units or fold systems where you shear the limbs of units or fracture the top and spur faults, and you develop orogenic gold deposits between units along these fold systems or in these faults. They can be steep fault fill veins, or they can be shallower extensional veins. Here you can see both. They tend to form coevally. As fluid pressure starts to reach rock pressure, you start to open these extensional style veins. Once rock pressure gets exceeded by fluid pressure, and it also exceeds the rock strength, you break the rocks, you have a seismic event, and you deposit your silica and your metals. Then you seal the fault. Then again, you build up these extensional faults. Then again, you fault fill veins, and you go back and forth. This is what's known as fluid cycling, and is very characteristic of orogenic gold, where you'll have hundreds of cycles over 2, 3, 5 million years developing these type of vein systems. The more complex, the better, because more complexity opens more space. This is another example from Western Australia, the Golden Mile, the largest Archean deposit. In a 10 million year time span, basically we had convergence, we formed a fold fault system, thrust faults and folds here. Then we switched to synostal strike slip along some of these thrust and fold limbs, and we formed the Golden Mile fault system here with these giant east load and west load systems and the giant open pit. Then we switch to thrust faulting again, and you can see more thrust faulting here. Then we changed to a dextral strike slip, and we developed the Mount Charlotte gold deposits over here adjacent to the Golden Mile deposits. So the more complex, the more tectonic changes, changing regional stresses, the more favorable for orogenic gold along these structures. And here you can see some examples of this. These are second order structures in Africa and Finland. Over here in Africa, you can see we have metasediments on one side, a bunch of phyllites. On this other side, we have metavolcanics. You can see they're bleached near the contact, and along this shear is where the mineralization is. Similarly, we can go to Finland. We have two metavolcanic units here. We have a shear zone of metasediments in between these, and that's where that Kipla mine is with 8 million ounces of gold along this shear. So you want to look for faulting between units. That's often what your second and third order structures are. If you're looking undercover, using your geophysics to find these contacts is a way we're discovering many of these deposits today. And most of that mineralization, again, moves during changes in far-field stresses. Tectonic change is critical. This is something we did in the Juneau area. We published this, I think, in 1991 in Nature, but this holds all the way back to Barberton at 3.2 billion years in South Africa. You need changes, and that allows fluids to flow. For example, we had orthogonal collision here. We were subducting a cooler plate along North America. We were subducting, we were metamorphosing the rocks. As I said, 3 to 4% of the rock changes to fluid. Basically, you have a large fluid volume in pore spaces as everything's held tight. You had a change of 56 to 55 million years to more oblique motion, a plate subduction. Oblique motion leads to strike-slip faulting along the faults and also to regional uplift. You start having regional uplift, you reduce rock pressure relative to fluid pressure, and fluids then move into the major fault, fracture, and start forming your orogenic gold deposits that then are uplifted to the surface over tens of millions of years. So changes in far-field stress is critical to orogenic gold. Now, any metamorphic belt with moderate to high temperature is going to form the right ingredients, your fluid and your gold, your metamorphic fluid that always carries gold. But if you don't have structure, you're not going to form orogenic gold deposits. This is the Seward Peninsula near Nome, Alaska. The biggest orogenic gold deposit out here was 27,000 ounces. Basically, you produced a lot of metamorphic fluid here, but it produced small high-grade veins all over the place because you didn't have that major structure to focus the fluid. You had great geomorphology, so that geomorphology led to 1 million ounces of gold being produced along the rivers, and then reconcentration of the gold along the ocean led to more than 6 million ounces of beach placer being discovered along the beaches of Nome during a historic gold rush. So you could still have great placer fields. Another example of this is the Klondike gold field in Yukon, Canada. 20 million ounces of gold recovered from alluvial concentrations and no lode production. So you need those large faults if you're going to have large lode deposits. The orogenic gold deposits generally are concentrated in green schist facies, and I'll talk about why in a little bit. But along these major faults, you want to look at your metamorphic setting. Where is the green schist facies? Because in this green schist facies, this is the area I showed you of Juneau, Alaska, is where the mines are located. You can look at Western Australia, almost all gold's in green schist. We can look at Canada and central Canada, all the gold's in green schist. So you want to look at green schist facies rocks. Now the gold mineralization here, you could see postdates to metamorphic cleavage. The gold is always later than metamorphism of the host rocks. But in an orogenic belt, in a mountain range, the metamorphism isn't the same everywhere. It's tens of millions of years apart because you're continually subducting, you're heating rocks at depth, you're creating a metamorphic fluid, and that fluid is moving up the faults into rocks that have passed the peak of metamorphism 5 or 10 or 15 million years earlier. So the fluids are being produced during metamorphism at depth and move into uplifting rocks that have already passed the peak of metamorphism. And that confuses people. Some people say, well, how can it be from a metamorphic fluid if the veins post-date metamorphism? They post-date metamorphism of their host rocks, but lower down, the rocks are undergoing metamorphism. So in the green schist along the faults, often we want to look for traps. If you have an older competent rock, like a granite, sitting in a less competent rock, such as a flysch or an argillite, it's very competent. It opens spaces, and that's where the fluids will go. This is the Alaska Juneau mine. This is all flysch or turbidites. This is a large metagabbro. There's a series of these. For scale, you can see a mine opening here. You could see how 95% of the veining is in this more competent granite. There's not a genetic association. The granite is 150 million years older than the gold, but it's a nice competent rock. It breaks real easy, and that's where your gold veins form. Similarly in Peru, the Pataz batholith is 20 million years older than the Pataz gold deposits, but they go into that competent intrusion. That's a physical trap. Similarly, we can have chemical traps. This is the 40 million ounce Homestake deposit, a map of that Paleoproterozoic deposit in the US and South Dakota. You could see these 3 units, but you could see all the 40 million ounces of gold is associated along these folds in one unit, the thin Homestake formation. Why? Fluids move up this anticline with these synclinal limbs, and they hit this unit, the Homestake unit. It's a banded iron formation. The gold is moving with sulfur. Sulfur carries gold in a metamorphic fluid. The sulfur hits the banded iron formation. The iron reacts with the sulfur, forms pyrite and arsenopyrite, and the gold drops out. So this iron-rich rock is what we call a chemical trap. So you want to think as you're exploring in the green schist along the fault, what rocks could be good physical traps? What rocks could be good chemical traps? Most orogenic gold deposits look like this. They form at mesozonal depths, usually 6 to 12 kilometer depth, the brittle ductile transition, and they'll show both brittle and ductile features. And as I showed this earlier, you'll have the fault fill veins as well as the extensional veins. Sometimes they'll be low sulfide. Sometimes you'll have a lot of sulfide if the chemical conditions are right. But you could see all these laminations or stylolites in here. These represent hundreds of pulses of fluids during earthquakes over 3, 4, 5 million years. It isn't just one event, like a magmatic event that may form a porphyry or an epithermal deposit. This represents pumping of fluids along a major fault during seismicity for many, many millions of years. The mineralogy in these mesozonal orogenic deposits, 6 to 12 kilometers, mostly every orogenic deposit has some pyrite, pyrrhotite, and arsenopyrite. Pyrite is dominant in Archean deposits and in intrusion-hosted deposits. Arsenopyrite tends to be dominant in more reduced rocks and sedimentary-hosted orogenic deposits. In orogenic gold deposits that form slightly hotter, above about 350 degrees, pyrrhotite is the dominant sulfide. Tungsten, tellurium, and bismuth are common in most orogenic deposits. It has nothing to do with magmatism. These can move in metamorphic fluids too. Low temperature orogenic deposits often have stibnite. Copper, lead, zinc are present in almost all orogenic gold deposits, but at very small levels. They're never recovered as byproducts because these are low salinity ore fluids and they just don't carry base metals. So you're not going to mine base metals from an orogenic gold deposit. You might mine tellurium or tungsten, especially as those are critical minerals today. The style can vary of orogenic gold. When you go to a mine and look at it, you might see in a very ductile rock, you might see something that looks like this. Just a second, let me get my dog out here. Henry, come. You might see something like this, where you see all these ribbons of stylolites. These represent many different earthquakes with rocks being pulled off the side. You might see this in an argillite. On the other side of the fault, if you're in a very brittle rock like a granite diorite, you might see a breccia. In a volcanic rock, you might see a brittle features like this, which are stockworks. These aren't different deposits. These are different styles, which partly reflect rock strength and partly reflect temperature. But you can go into a mine, and if there's a fault between a granite diorite and an argillite, on one side it'll look like this, on the other side it'll look like this. So there are many different styles even in the same deposit. A guy named Sandy Colvine pointed this out a long time ago. Most of the deposits look like I just showed you, very brittle ductile features, extensional and veins. But very shallow deposits at lower temperature will all be brittle, and they'll be pretty much just breccia and stockworks. When you get down below about 12 kilometers, you're in hotter environment. Rocks are very ductile, and they slide, and you don't build up the big pressures to fracture the rocks and drop a lot of silica. So you'll see more replacement style mineralization. So depending on the depth of orogenic gold, most deposits show that brittle, ductile, laminated type extensional fault-filled features. But the shallowest deposits are more stockwork and breccia. The deeper deposits, more replacement style. The alteration of orogenic gold is going to be sericite, carbonate, sulfide. The sericite is potassium in the fluid. It reacts with other silicates and forms sericite. Often may bleach the rocks adjacent to the deposit. And also the potassium gives you sericite, which you can date using argon methods. There's a lot of CO2 in orogenic gold deposits. It's very unique to this type of fluid. So carbonate alteration, often anchorite or ferrandolomite, is very common. And also because there's a lot of sulfur, you sulfidize the iron in the wall rocks and you'll get pyrite and arsenopyrite in the wall rocks. And this may have lower levels of gold compared to what's in the vein. But when the price of gold is high, this alteration actually becomes ore. Mostly you have carbonate and sericite, but at higher temperature orogenic gold where you get pyrrhotite, you also at deeper levels where you have this replacement style mineralization, such as you see here in Red Lake, Canada, or here in Western Australia, you don't get the big quartz veins, and you may even get calcsilicates. These are skarn minerals, but these are not a skarn deposit. These are not associated with granites. They're not in carbonate. They're just high temperature, amphibole, diopside. You just can form these at higher temperature. So the alteration may change as you go to higher temperature. And this is, again, what some of these deposits look like. This is Muruntau, the world's biggest orogenic gold deposit in Uzbekistan. Kolar, the big one in India. You see some of this sulfidation here in Detour Lake in Canada. So these are a lot less distinct than the shallow orogenic gold deposits because they don't have the big quartz veins. And again, you can see some of the sulfidation. This is a banded iron formation in one of these. And you can see how the sulfide, which actually has gold in it, has sulfidized the banded iron formation, and you just don't see a lot of quartz. And this is an example. This is from Kumtar and Kyrgyzstan. This is what a shallow orogenic gold deposit would look like. You see stockworks and breccia. This shouldn't be confused with epithermal deposits. These are metamorphic waters. They're high in CO2, and they just form this style of brittle orogenic gold. The interesting thing about those shallow epizonal deposits is if you're in the epizonal environment like at 3 kilometers and you're starting to deposit lower temperature minerals like massive stibnite with the gold, sometimes you may just see the massive stibnite and go, well, that's an epithermal deposit. I see stibnite. But no, you can have stibnite in orogenic gold deposits. And for example, this is Donlin Creek, Alaska. Originally, they mined massive stibnite because it was easy. They saw it right at the surface. Then they noticed some anomalous gold in it, and they drilled down a little, and now it's a 40 million ounce epizonal orogenic gold deposit. Similar, these are the great deposits in Central Asia, orogenic gold, Murantau, Zarmatan, Kumtar. In between in southwest Kyrgyzstan are all these antimony deposits that the Russians mined solely for antimony. But given this belt here, my guess is these are going to be shallow orogenic deposits that have potential similar to these world-class deeper orogenic gold deposits that don't have the same amount of antimony. So epizonal deposits are important targets and also do produce a large amount of the world's antimony. Now, there's a lot of evidence that it's hard for many people to understand the metamorphic water. People say, you can't have a lot of water during metamorphism. But again, 3 to 4% of a mountain range changes the fluid during metamorphism, which is a heck of a lot of fluid and is why we have orogenic gold in any moderate or high temperature belt. If we analyze fluid inclusions, we see not just CO2 in the ore fluids for orogenic gold, but nitrogen, H2S, and methane. These are the same gases that a metamorphic geologist will tell you they always see when they're looking at a metamorphic fluid. They don't care about ore deposits. This is a medium temperature metamorphic fluid when you devolatilize a rock. Where does the H2S come from? Well, if you look at your, say, an argillite, it may have 8 parts per billion gold, but that gold's not in the quartz, it's not in the feldspar, it's not in the chlorite. It's in those opaques you see in there, that diagenetic pyrite that formed on the ocean floor. If you hit it with a laser, that pyrite, it may have 600 ppb gold or 1 part per million gold. That's why your rock has 8 ppb gold. So when you devolatilize that rock, pyrite converts to pyrrhotite at green schistoamphibolite facies boundaries. And so the H2S moves out of the pyrite because there's less sulfur in pyrrhotite. And so you always have H2S in an ore fluid and in a metamorphic fluid. And that H2S also carries the gold out of the diagenetic pyrite. So gold is inherent to a metamorphic fluid. And so both fluid inclusion information as well as oxygen, hydrogen, sulfur data all argue for a metamorphic model for orogenic gold. If you go to a belt such as here on the South Island, New Zealand, and you look at one lithology, as you go to higher metamorphic temperatures, all these elements that are enriched in these gold deposits in these rocks get depleted. First mercury at low temperature, then things like gold, silver, tungsten, antimony, arsenic. By the time you get up into amphibolite facies, all these elements have moved out of the rock and into your metamorphic fluid. And that's the source of metals and orogenic gold. And you're not just releasing metals from pyrite or tungsten from rutile that's being metamorphosed, but you're also releasing lots of fluid from chlorite and biotite during that metamorphism to give you 3 to 4% of the rock volume being fluid. And you're also producing a lot of CO2 because organic material that's in the rocks is being metamorphosed and releases the carbon. So that's how we develop a metamorphic fluid that forms your orogenic gold deposits. Now you may pick up economic geology or all these journal articles in all sorts of journals today, and they're analyzing every isotope that I can't even pronounce, rare gases, whatever, and they're coming up with all sorts of models for orogenic gold, different than metamorphic models. But there's all sorts of problems with these. For example, this is a gold-bearing quartz. All these lines are secondary and fluid inclusions. People squeeze these or heat these to get the fluid out, measure it, and they say, oh, we get argon or helium or some isotopes, and they give a magmatic signature or some other type of signature. Well, these are all yesterday's rainwater trapped as the vein is uplifting. These secondary inclusions that make up 99% of an orogenic gold quartz vein don't have the fluid that formed the deposited the gold in silica. So these bulk extraction methods make no sense. Many people are doing all sorts of isotopes of, say, sulfides and things like that. They're analyzing, say, mercury isotopes and say, oh, yeah, the mercury isotopes or the pyrite basically match mantle numbers, so the gold must come from the mantle. But they also match sedimentary rocks being metamorphosed. So we don't know what those numbers are even telling us, and they can tell us a lot of different things. So you have to be careful. There's a lot of garbage coming out in the literature today, and much of it is fairly meaningless. Its sulfur isotopes vary over geologic time, and that's because the sulfur is coming out of the country rocks, and the sulfur in the country rocks varies with time. There's no magic magmatic number like 0 plus or minus 3 for magmatic type deposits. For meta-orogenic deposits, sulfur varies over time, consistent with only a metamorphic fluid. Some workers like to say, I know where the gold came from by doing lead isotopes on galena or pyrite or some other sulfide that's in the gold-bearing quartz vein. But I showed you those two deposits on opposite sides of that fault in Juneau earlier. They're in two different terrains, and look, their lead isotopes are totally different. That's because most of the lead is not moving in these ore fluids. These are low salinities. I said they don't carry copper, lead, zinc. In the alteration at the site of deposition on opposite sides of a fault, you're breaking down feldspar. You may form cerussite when the feldspar breaks down, and the loose lead goes to give you the little galena in the fluid. So when you measure a lot of these isotopes at the site of gold deposition, you're measuring the isotopic signature of the host rock and not anything in a source area, the source of the gold, the source of the fluid. So you have to be careful. A lot of these studies are meaningless. Also, people like to have one model. Now, we know that the gold is metamorphic in origin, but one model doesn't fit. For example, where I work in Alaska, you have crustal thickening, hot rocks over low rocks, over hot rocks thrust over cold rocks. You develop what's called an inverted metamorphic sequence, where you go from amphibolite to green schist and you produce the fluids. Another area I've worked in Alaska, you can have slab rollback and extensional heating, and you can have gold in normal faults. Another place I've worked, we have subduction of a slab window spreading between plates. You can have mantle plumes in the Archean. You can have contact metamorphism on a regional basis. The key is the first time you heat oceanic rocks through that green schist amphibolite window of 400 or 500 degrees, you produce the fluids to form orogenic gold. And one model doesn't fit everywhere. The key is basically whatever you have to study the tectonics and geology of the area you're studying, and whatever tectonic process metamorphoses those rocks for the first time is the key. And all these different models are important in different places. As I said earlier, the orogenic gold has formed all through Earth's history. 75% of the Earth's crust has formed in the late Archean or Paleoproterozoic during plume events. And that's when 50% of our orogenic gold has formed during the growth of these two supercontinents, Quinoa Land and Columbia. The last 25% of our planet has formed in the last 1.6 billion years. Those are the ribbon continents along the edge of the cratons, the margins to our continents, the metasediment terrains that surround the continents. So that's when we formed the last 25% of our Earth's continents. And you can see the other half of orogenic gold forms during this time. But there is no gold in Rodinia. So why? This was a large accretionary group of continental margins that formed 1.6 to say about 1.0 billion years. But there's no orogenic gold. You would not explore in rocks of that age. Why? Well, we preserve our orogenic gold that formed earlier in the cratons. This is the Grenville origin. This is the oldest accreted origins. Again, 1.6, 1.7 to 1.0 billion years. It's been reworked and metamorphosed over and over again. And it's mostly exposing rocks that were 20 or 25 kilometers. So it not only lost its intrusion-related deposits, it's also lost its orogenic gold deposits because most of these rocks are so deep. There are a few areas left of green schist rock that haven't eroded away, and the most important of these is actually on the Bolivia, Western Brazil border, where there are some orogenic gold deposits of that Mesoproterozoic and early Neoproterozoic age. But for the most part, you would not explore in this age rocks. People like to say, what is the precipitation mechanism for orogenic gold? There's never just one precipitation mechanism. The fracturing and the drop in pressure causes the silica to drop out of solution. That's why we have all these quartz veins in the mesozonal orogenic gold environment. But you could see here, drops in pressure when gold is traveling with sulfur don't cause a drop in gold solubility. Similarly, unlike when gold's with chlorine and magmatic systems and temperature drops are important, drop in temperature when gold is with H2S, with HS2, doesn't cause gold to come out of solution. So the silica comes out because of the pressure drop, but the gold comes out because during the pressure drop, other chemical changes happen. The fluids may react with the wall rock and you have sulfidation, or if you have gold here and you go into, say, a very oxidized rock like a granite, you could oxidize the fluid, go into an argillite, you reduce the fluid, you can change the pH when you lose that silica, react with wall rock, and that all those reduce the solubility of gold and it comes out of solution. So the key is changes in pressure, get the silica out, and then at the same time changes in pH, FO2, and sulfur get the metals out. So there's never just one precipitation mechanism. Gold often comes in late. Next pulse of fluid may dissolve some of the silica because silica dissolves very easy in fluid. It may dissolve the fluid. You may form stylolites in that fluid moving along there, reacting with the quartz and any earlier mineralization may deposit your gold or sulfides along those conduits. But actually, what does paragenesis even mean in orogenic gold? For the most part, it's fairly useless. Paragenesis means something on a polished section scale, but we're talking about hundreds of pulses of fluids over millions of years forming veins like this. So you may deposit some quartz, then some gold, then some sulfides, then more quartz, then some gold, then some stibnite, then more quartz, then more sulfide, then more quartz. So the paragenesis is that you see and that gets reported is just on the polished section, but it's very complicated because things are happening over and over in the formation of an economic vein system. When you look at these, often you see things like tellurides and stibnite always looking paragenetically late. They always seem to cut pyrite or arsenopyrite that is more massive and been deposited earlier. And so many workers like to say tellurides and stibnite are unrelated and they reflect a second event from another source in the orogenic gold deposits. But how real is that? To get tellurium and antimony out of solution, two things can happen. You can drop the temperature, which doesn't happen, or you can reduce the fluid. So if you have a lot of pyrite or arsenopyrite there, and a fluid comes in and reacts with the early pyrite or arsenopyrite, it'll get reduced. And so your calaverite, your gold tellurides, or native tellurium and gold will drop out and be in that early pyrite and arsenopyrite. And the same for antimony and your stibnite. So it doesn't mean there's another unrelated event. You're forming your orogenic gold, and then there must be a magmatic event bringing in the tellurides. No, tellurides are present in almost every orogenic gold deposit, even often though in small amounts. But that doesn't mean they're coming from a separate magma. It just means the fluid is reacting with earlier deposited metals in there and dropping out the tellurium. Many orogenic gold deposits have broad halos of a mineral. You can't go into North China without seeing halos hundreds of meters wide of K feldspar with your sericite, pyrite, quartz alteration further in the halos surrounding the veins. You can't go to Finland without finding an orogenic gold deposit. They're all surrounded by areas of albertization. You can't go to central Canada without finding your veins surrounded by broad areas of carbonate alteration. Are these different fluids that form this early alteration that's so broad? It's hard to believe it is. Most likely the first fluids that come up the fault react with the wall rocks. And depending on the wall rock chemistry and the fluid chemistry, you might get K feldspar, you might get albite, you might get carbonate, but they give you broad halos. Then the next pulse of fluid comes up, and this early alteration has made the rocks more competent. So the next pulse fractures these more easy that have been altered and allows the silica to come out of solution because you have big pressure drops by the fracturing. Then you deposit the silica, and that leads to then the fluids coming in, dissolving some quartz, forming the stylolites, depositing the gold and the sulfides, etc. One thing you're going to see in the literature that's filling the pages of economic geology and elsewhere is we're now dating every mineral with all sorts of isotope systems. And for example, this is a small vein here in Finland that someone dated. And they came up with 5 ages spread over 100 million years. And 3 of these are when things are tectonically dead. Does that make geologic sense that the same minerals came in at 4 times with the same fluid and sometimes nothing was happening? Basically, instead of questioning, the measurements are good, but we don't understand isotope resetting well. During the history of these veins, things happen to the isotope ratios. So rather than always accepting ages because it's a complex isotope system, so it must be right. Maybe think, well, there's no geologic reason to explain this date we got. Maybe only one of the ages fits geologically, and we should question some of the other ages. So be careful. We're starting to get every orogenic gold deposit forming on 4 or 5 different events spread tens to hundreds of millions of years apart, and that makes no sense. Another point that I stressed earlier is our definition of orogenic gold has changed. When I started studying these, the 25 largest orogenic gold deposits were thought of as high grade, low tonnage, as opposed to, say, a porphyry system. But today, these are our 25 highest, biggest 25 biggest orogenic gold producers. You can see we're now going to much lower grades, but much higher tonnages. And we're mining these at the same grades and tonnages as we're mining some of the world gold-bearing porphyries. So you no longer could say orogenic gold are simply lower tonnage deposits, but must have higher grades, because sustainable issues are so important today in investing in mines, helping the local community. Environmental issues, it's a bigger investment, and we can also mine lower grade ores with better chemical methods. So we change what we mine in orogenic gold. For example, I mentioned Morro de Oro, Paracatu in Brazil, 20 million ounces at 400 ppb gold. That's incredible low grades, but it's a flat-lying deposit, so it's amenable to open mining in a drier climate in Brazil, where there's a history of lead zinc mining nearby, so the community was very pro-mining. But part of the problems are, I used to go out to an orogenic gold deposit, look at something like this and say, I know what that is. That's an orogenic gold deposit. Now you go out and they're mining something like this. There's some pyrite and arsenopyrite, and there may be gold in here. They're mining this at 500 ppb. And people say, oh, it must be intrusion related, or it must be a Carlin type deposit. But you're in a metamorphic environment. There's a large fault nearby. Maybe you haven't found the quartz vein yet. You're just mining all these sulfides that are distal lower grade alteration to your typical orogenic quartz vein. So this too has led to a lot of confusion in the literature, and you have to be very careful. Just because someone says something is, say, a Carlin deposit, don't believe it, read it carefully. People like to say, what makes a giant orogenic gold deposit? You want to look for anything weird, anything different. This is Muruntau, again, the largest orogenic deposit in the world, 185 million ounces in Uzbekistan. Things that stick out is a weird jog. There's a fault that goes east-west for 2,500 kilometers. There's a large jog in it you see on the map of Asia that sticks out like a sore thumb, and Muruntau sits where that large jog is. On the north side of Muruntau, there's carbonate. Normally, you don't see carbonate in an active margin, but this was a piece of Siberia that floated in before these clastic sediments were added here. So maybe having carbonate, which is very unusual, is important because it's karst-type rock, and maybe you develop better flow through it. The Russians argued this argillite has a high background of 100 ppb gold, which is a huge background for an argillite. And if that was metamorphosed, maybe that's why Muruntau is here. Maybe one of these is important, maybe all three. But these are the kind of things to think about when you say, why is one deposit so large? Why is an area so gold rich? We look at West Africa. Every gold deposit in West Africa is associated with lots of carbonaceous matter. The faults in West Africa formed when you broke up an Archean craton. It pulled apart. You had these Paleoproterozoic basins. They were interior basins, so they got lots of diagenetic pyrite in these, lots of organic matter that concentrates gold and sulfur, and so you metamorphose that, and that can lead to a huge gold endowment because you have all that background gold throughout these basinal sediments. Nevertheless, one last thing I want to talk about in the last, I'll give you 10 more minutes here and then we can do questions, is workers still love granites no matter what. You'll see half the papers coming out now in the literature talk about orogenic gold being related to magma. A guy that Werner Giggenbach, famous magmatist, said this, even though he's a magmatist, in his SEG presentation in 1992. He said, you know, if economic geologists don't know where a mineral deposit came from, they just put an arrow on their map and point downward and say, there must be a granite there, it must be the source. And certainly there's a spatial and genetic association between granites and orogeny, just like with metamorphic fluids and orogeny. But if we look worldwide, some granites are 20 million years older than the gold, some are 20 million years younger than the gold, some are the same age, some are S-type, some are I-type. You know, the South Island, New Zealand, there's no granites whatsoever near the orogenic gold. So there's nothing consistent. Both gold and granites are produced during orogeny. And often dikes and sills will come up the same structures that the mineralization will come up tens of millions of years apart. If you go to any large pit, you may see lampopheres, and workers like to say, see, there's a mantle connection. There's lampophere dikes associated with these orogenic gold. But all lampophere dikes is you have a big fault connected to the mantle, and lampophere magmas came up at one time, and orogenic gold came into that fault at another time. There's not a genetic association, but people love it. So you'll pick up economic geology, and in the last 10 years, this Canadian Malartic deposit, a giant deposit being mined in central Canada on a second-order fault of this main fault, a clear orogenic deposit, depending whose paper you pick up, one calls it a porphyry gold deposit, one calls it a cyanide-associated disseminated deposit, another calls it oxidized intrusion-related, another has mesozonal replacement, because they're mining alteration adjacent to the historic high-grade vein. They also hit some porphyries, pre-gold porphyries that are also slightly sulfidized in this pit that they put around the historic deposit. But it's an orogenic gold deposit. But, you know, it's difficult to know because you'll Google this deposit and economic geology and you'll find different authors calling it different things. Does magma even matter? I'll say no, because this is where I was talking about the Otago schist belt on the South Island, New Zealand. Here's 8 million ounce McRae's deposit. There's not a granite anywhere here. This is an example where you got to 500 to 600 degrees for metamorphism, but you never got hot enough for magmatism. So this shows you don't need magmatism to form orogenic gold. Yeah, I was recently working in Colombia. The Segovia Gold Belt is a world-class gold belt in the margin of a subduction-related batholith in Colombia. Looks like this, like many orogenic deposits. 160 million years ago, this batholith was in place. The gold deposits are only 80 million years, but they sit adjacent to this 80 million year old batholith. And so many workers have argued this is the cause of these gold deposits. This is where the fluids have come from. And many people call this an intrusion-related gold deposit, intrusion-related gold belt, the Segovia Gold Belt. But I told you earlier, things move. These are long strike slip systems. 80 million years ago, this supposedly causative intrusion for these veins was sitting near you guys in Ecuador, 1,000 kilometers away. And you have to look at the map at 80 million years, and you will see this batholith was in place nowhere near these gold deposits, but was way far away from Colombia at the time. And many of these we need to look at reconstructions. Just quickly, this is West Africa, 300 million ounces of gold. Well, 300 million ounces of gold. Here's Northern South America. At one time, these were all tied here before Africa and South America pulled apart, all part of one great gold province. I talked about Muruntau, the world's biggest orogenic gold deposit. It formed at or anywhere from 6 to 10 kilometers. The Russians put a deep drill hole down next to Murintal, and four kilometers below that, they found a fresh plug that's unaltered. And many workers argue this is the source of this giant gold deposit. Number one, there's no alteration. Number two, it's a small plug. But number three, at those depths, people don't realize a magma will not release fluid. Water dissolves in magma. It's controlled by pressure. Until you get up till about 6 kilometers, which are your deepest copper porphyries, water stays dissolved in melt. So these deposits that form at 6, 8, 10 kilometers cannot form for magmatic fluid because any granites at this depth will still have their water dissolved in the granite. Just quickly, I know we're running out of time. If you took a hydrous magma that, say, could form a porphyry, but you start uplifting it, it may originally have 58% CO2, 42% water. It starts releasing a little water from magma as it goes up. But orogenic gold deposits have 85% CO2 and 85% water and 15% CO2. That doesn't reach that composition till you get to about 1.5 kilobars pressure, or about 5 kilometers. And you don't start releasing large volumes of water till you, typical that you can form a porphyry till you get to those levels. So, So at these depths of magma moving up, you're just not going to release a lot of water and CO2 to form an orogenic gold deposit or a porphyry. That's why your shallowest porphyries are 5 kilometers and your orogenic gold deposits that form here cannot be magmatic. And even if you had a superhydrous magma, which is more than most people say for a porphyry, which can have 4 or 5% water, if you had one that, say, had 10%, the magmas crystallize inward, fluid water moves up between the crystals and the mush and come out the top at shallow levels. That's why your deepest copper porphyries are at 5 kilometers, and those with gold, the deepest gold-bearing porphyries that are economic are about 3 kilometers. So these orogenic gold deposits are not magmatic, despite what you read in the literature. People like to talk about intrusion-related orogenic gold deposits. If you have a large gold deposit that formed below 3 and 5 kilometers, you can put it in this bag and say it doesn't exist. You may also see some recent papers in economic geology relating orogenic gold to mantle lithosphere. Couple of problems relating orogenic gold to mantle. First off, I work in Western North America. Here's the edge of Western North America, the continental lithosphere. The accreted terrains out there are all underlain by accreted sediment and accreted oceanic crust, such as I showed you that Juno example. All these deposits sit above these oceanic rocks, not above subcontinental lithospheric mantle, even though people say that's what you need for orogenic gold. It may be important for porphyry magmas, but not for orogenic gold. A second problem with a mantle model is people say, well, if it's not magmatic, you could still have these mantle fluids move up. But if you have fluid in the mantle, what does it do? It doesn't move up. It forms magma. That's how you form mantle magmas. The water melts the mantle, goes into the magmas, moves up, and at those pressures doesn't come out of magma till you get to 1.5 or 2 kilobar pressure or 5, 6 kilometers. So a mantle model is totally impossible for orogenic gold, but too often economic geologists ignore what the petrologists tell us. So just a few summary slides. Orogenic gold deposits can form a new crust. It can be a forearc or a back arc, but you add new crust to a growing continent, and when you heat it through any method, through green schistoamphibolite for the first time. You create the ingredients to form orogenic gold, and if you can focus these along major structures, you're going to form orogenic gold. That formed during thermal events in the late Archean and Paleoproterozoic, and also is widespread in the Phanerozoic. We have our boring billion here, where all our rocks that are exposed to this age are too deep even for orogenic gold. We want to think about structure. We want to think about metamorphism. We want to talk about traps. The gold is originally diagenetic on the seafloor, but gets heated during metamorphism. And today we're mining lower grade orogenic gold because things like economics, politics, and perception are important sustainability issues that are critical. You'll read a lot in economic geology and other journals that is science fiction about. There's no association with magmatism. Tungsten, bismuth, and tellurium don't indicate a magmatic metal source. It can be a metamorphic source also. Radiogenic isotopes don't tell us where the gold came from. There is no mantle connection. Separate events spread over hundreds of millions of years are garbage. Don't believe them. And saying late phases like telluride, sulfur salts, stibnites have come from a different source is often wrong. And just a few last slides. Forget these in red. This is the Witwater Strand. But you could see for orogenic gold, we're starting to look undercover. The prospectors found the easy ones. Now we need to use our geologic knowledge that you guys are getting to look undercover for orogenic gold in the upper hundreds of meters. We can use geophysics, such as here in Mauritania, look for fault intersections, such as where Kinross sits. You can see this country, geophysics is what you need to look undercover. In Australia, they trace under a thin basalt cover with geophysics and sampling springs, and they found extensions of this structure under the basalt to find other prospects. In China, they traced the fault off into the sea, went below 700 meters of seawater, intersect the structure, and have a huge resource along that structure under the sea. In South America, northern South America, you have thick regolith. Any of you that study geomorphology, understanding regolith and movement of regolith is critical, weathering and erosion, for understanding orogenic gold below this cover. I've been working in Newfoundland and Finland. People are now looking below the base, looking at the base of Till to lead to huge gold rushes in Newfoundland and central Lapland, where before, no major gold deposits were recognized. This recent discovery, Ikari, which is 4 million ounces now, one base of Till sample with just 200 ppb below 5 to 40 meters of the Till on the bedrock is what led to that 4 million ounce discovery. So understanding geomorph, glacial geology, geophysics, geochemistry are all going to be important to us in exploring for orogenic gold in the future. So that's sort of basically what I have to say on this, and I'm happy to take questions. I'll get rid of this PowerPoint, and thanks to everybody, and if there are questions, I'll be happy to take them. I'm not sure. Let me see if I can get it. I probably should. Let me see. Oh, this one. I said, oh, this next to the screen sharing. Oh, on my open chat. Okay. So I'll go to the top one. Uh-oh, someone couldn't hear me. Okay. Is it possible to precipitate gold at more than 500 degrees? Under what environment or conditions could it be possible? That's a good question. Certainly in the orogenic world, 500 would be the highest temperature and it would be sulfidation of the wall rock. I would hate to say it's higher than that. Off the top of my head, I don't think it is possible. I know some recent papers by Andy Tompkins and the Chinese talked about forming orogenic gold at 600 degrees or something, but I think 500 would be the highest, and you're very ductile, so you wouldn't see any sort of veining or stockwork, so it would all just be sulfidation of iron-rich rocks. Can the origin of alluvial gold be distinguished, whether orogenic, epithermal, or skarn, etc.? You know, people like to do this with geochemistry of alluvial samples, but so often, so much changes in the secondary environment along the creeks that from what I've seen, it is pretty difficult, but I don't think that would be as important as looking at the geology of the region you're in and deciding whether, okay, I'm in a metamorphic belt. The source is going to be orogenic. There's large faults. There's other orogenic systems here. That got to be the source. Or, you know, I'm in a magmatic belt, so it's probably not going to be orogenic, especially because there's no metamorphic rocks exposed. For the most part, most of the world's alluvial gold deposits are associated with orogenic gold, whether they go anywhere from eastern Russia and Siberia all the way down to the South Island, New Zealand, whether you go from Nome, Alaska, down into some of the things going from the Pataz Belt into the Amazon. Those are related to orogenic gold. So mostly the younger orogenic gold deposits are responsible for most of the world's gold deposit that's alluvial. Some are preserved in paleoplaces. Certainly, there's one in Africa and there's another in Brazil, paleoplacer, that are related to orogenic gold. The world's great paleoplacer, the Witwatersrand, was preserved under basalt. It produced a third of the gold ever mined on this planet. We have no idea what the source of that was and why so much of the world's gold was concentrated in one basin in South Africa. So all we need is metamorphic paragenesis where gold minerals are metamorphic too. I'm not sure I understand that, but basically all we need is metamorphism. If it's low temperature metamorphism, like on a blue schist gradient, you may get to 350 degrees and 20, 30, 40 kilometers depth, but you never get hot enough to form orogenic gold. So anywhere you have a green schist or even a higher temperature gradient of 20 to 30 degrees or higher per kilometer, you're always going to form orogenic gold, and the key will be concentrating it. And the paragenesis is always questionable what it means. You can define your paragenesis when you look at the deposit and polished section, but just because I see some gold later than some pyrite, there still may be later pyrite or silica coming in after that gold. So again, the paragenesis is just what you see in that polished section, but not on the deposit. What isotopes help in understanding orogenic gold? The only ones I am comfortable with are, number one is sulfur, because sulfur will tell you something about the source rock sulfur, which usually is the age, the sulfur isotopic signature of the host rock at the time the host rock deposited the sulfur and the diagenetic pyrite on the ocean floor. For example, if your host rock is 200 million years old and your gold deposit is 50 million years old, the host rock sulfur signature of pyrite at that age is what you would get. And that's why sulfur varies through geologic time for orogenic gold, depending on the age of the host rocks. Oxygen and hydrogen certainly are very consistent with a metamorphic fluid, and a very heavy oxygen is a real key. When I started working on the antimony deposits, people were calling these epithermal, and then I would analyze the oxygen isotopes. They would always be plus 25, plus 30, only consistent at that low temperature with an oxygen fluid value of plus 10, much heavier than an epithermal deposit. So oxygen, hydrogen, sulfur, I think are all useful. Beyond that, I think a lot of the stuff out there is garbage. I haven't been sold on anything. There's a debate about the name metamorphic deposits receive. Do you agree with the name orogenic? You have to give it a name. Certainly metamorphic would be a good name too, because these are related to metamorphism, but so many people still try to relate these to granites. We probably don't want to use metamorphic. People used to use the name mesothermal, but mesothermal is a name Lindgren coined for 200 to 300 degrees and 1.2 to 3.6 kilometers. These all form deeper, and most formed hotter than that. And they would have been called hypothermal, not mesothermal, under that old terminology. So you have to come up with a name. These represent fluids that are regional, part of orogeny. It was coined by a guy named J.K. Bolke in 92. And it's probably the best name. I think it's pretty well stuck in the literature. There are many cases in which there are no notions, but metamorphism related to the squeeze could create the same. For example, I'm not all that familiar with the Warrawana deposit, but I certainly think, plutons, contact metamorphism can do the same if you have enough area that's contact metamorphism. If you put a pluton or a large pluton system or magmatic system or batholith into some rocks, and the heat from those first cooks the rocks through that magic sulfur gold temperature window, I think there's no reason you can't form orogenic gold deposits that way. What geochemical indicators are used to identify orogenic gold? Basically, you need to do a pilot study wherever you work, because it varies wherever you are. In Western Australia, tellurium gives the broadest halos. In Alaska, where I've worked, arsenic and tungsten have given the broadest halos. Elsewhere, antimony does. So what I would always say to do is, depending what sample media you're interested in, lithogeochemistry, soils, waters, whatever you're using, stream sediments, heavy mineral concentrates, go out and do a pilot study, at your known occurrences, because nothing is consistent. It varies wherever you are geographically. Between the epizonal and mesozonal environments, the associated gold and antimony tends to be common and should be differentiated. I worked on orogenic deposits in the Yulgan that show book-like features where gold is the main mineral in ductile structures. How in the Pilbara, because it can mask the real value of gold. There are shallow environments of brittleness. Apart from the stibnite and gold, the only mineral overall mineral component with no significant extensions. What level system are we standing at before making the decision to drill deeper or not? That's a good question. It's hard to precipitate a lot of native mercury and the metallic antimony, maybe weathering of the stibnite, maybe some conditions. You put out a hell of a lot of native mercury. Now, I see it sometimes, but not up to 22%. Some have stibnite. A lot of these shallow deposits have orostibite, which is hard to recover, and the gold is mixed in solid solution with the stibnite. But the main thing is you are at shallow levels, and if it looks like a favorable large structure and you're in a gold belt, it probably is worth drilling down on. You may look at Bridge River, the largest orogenic gold deposit in the Canadian Cordillera. You have The Braylon Pioneer 4.5 million ounce gold deposits in shallower levels just adjacent to it on other faults. And they're drilling the gold antimony properties on those right now. So certainly, no matter what the antimony is, it's going to be a lower temperature environment. It's going to be shallow. And just like any gold deposit, I would not write it off. It's not going to be an epithermal deposit. It's going to be epizonal orogenic. We had no tellurium or solarium, always below detection limits. And, that may be the case, but the majority of these deposits, as people are doing more and more, computer-based scanning of deposits, tellurides are seen more and more in the orogenic deposits. And it may just be a grain here or there of calaverite or native tellurium or bismuth-lead tellurium, but it's showing up in the majority of these deposits today. Tanya, remember everybody was puzzled by the lack of intrusives near Muruntau. They thought it was just sitting deep and were looking for geophysics. Yes, and they still are, and they still argue about intrusions at Muruntau. But if Muruntau formed at 6 to 10 kilometers, and all right, you have an intrusion, say put it at 8 kilometers. At 8 kilometers, any water is still going to be dissolved and melt because pressure controls it. And you're not going to put out so much water with so much gold to form a giant deposit because that water is not going to leave a magma at those depths. And, that may or may not be something economic geologists like to hear, but if you read the petrology literature, most petrologists are not going to have a lot of water coming out of magma at those kind of levels. Next, the relationship between the structure and geochemical influence on orogenic. Are they geochemical? Let me see. Are they geochemical in the golders over these batholiths? That's something that would take a while for me to look at and address because I'm not familiar with all those batholiths. But I really think the key to all those is structural control in the Eastern Cordillera of Peru. Those batholiths are nice, competent bodies and good hosts. I know some recent workers from Western Australia have recently talked about intersecting structures as being critical, but they talk about they show these structures coming from the Amazon craton all the way into the Eastern Cordillera. And I don't know if those structures were Paleoproterozoic structures in the Amazon craton. I still don't see how they went into the Eastern Cordillera, but I think structure and rheology are the keys to those batholiths. How can we work on lithogeochemistry of alteration when host rocks correspond to... Okay, let me see. How can one work on lithogeochemistry when the host rock corresponds to politic schist, rich in metamorphic muscovites? A lot of that one might do with using scanning, and the metamorphic muscovite may still have its signature that's metamorphic or detrital, and the hydrothermal micas may have some changes. Often with biotites, I know the hydrothermal biotites also often have more sodium because the potassium in the bio ends up going into the hydrothermal muscovites. And the hydrothermal muscovites might also have some differences from the, detrital and metamorphic muscovites. And that's probably what most people now are doing with the muscovites, scanning them to see how they differ. And again, thank you. And yeah, anyone wants to send questions or wants any literature, anything, I'm always glad to answer emails. 2 questions. Do you think a good orogenic gold deposit can be generated on low dip faults? Absolutely. There are many examples. People like to have these on high dip faults. But we recently wrote a paper on a deposit in Central America in economic geology on a low dip fault. And also You look at McRae's, that's the best example of any. That's a low dip fault on the South Island, New Zealand with 8 million ounces. And in the right conditions, especially if you seal a fault and can build up pressures on these, you can form these deposits. Often you don't get the huge pressure drops, and many of these may have more disseminated style mineralization, such as McRae's. What geophysical methods are effective? I think any method you use can be effective. I've seen them all used. I mean, you might look for electro methods for looking at graphite. That often is where the shearing is, or hydrothermal graphite, which where the faults are and the shearing. But even gravity or magnetic shows you boundaries between units, and boundaries between units are important recognition of faults. These are low sulfide, so you're not going to find the ore deposits with your geophysics often, but you're going to be able to trace the structures, and the structures host the deposits. My email is my initials and last name, rjgoldfarb @mac.com. Is it possible to find minerals like bornite or covellite? Would it make sense to do due to what does a WO anomaly mean? Whoop, I don't know what a WO is tungsten. I don't know what a WO anomaly is. Bornite and covellite are very, very rare. Sometimes they may be supergene, like you say. I agree with you, Laura. But for the most part, you would find chalcopyrite as the main sulfide phase. And I don't know a single orogenic gold deposit where chalcopyrite is being mined from orogenic gold. Oh, Mali anomaly. Some of these have Mali. You don't know if it's, picking a little Mali up from the black shales. Sometimes in the intrusions, it might pick it up. A lot of these that I've seen in the intrusions have traces of Mali. Sometimes you have a buttload of Mali in there. Sometimes the Mali is there earlier in the intrusion in veins that they see in the deposits and will be much older, and it's a problem when someone does rhenium osmium on that Mali that's in the host intrusion, but the orogenic gold deposits in, so you have to be careful. But anyway, I'm going to run because my dogs are angry that I got to feed them, and it's past their food time. But, definitely email me if I can help with anything. Oh, one more question. Is it possible to find bismuth in orogenic? But bismuth is very common in orogenic gold deposits. People never analyzed for low-level bismuth, but it was always there. Bismuth substitutes for lead and galena, and also bismuth goes into the tellurides. And when the first reduced intrusion-related deposits went into production, Fort Knox in Alaska, which I don't have time to get into those deposits, but people said, because there were no sulfides in the veins at Fort Knox, oh, I see native bismuth and bismuth tellurides. So bismuth is the key to defining an intrusion-related deposit. And so people started reanalyzing all the orogenic gold deposits for low-level bismuth, and they started detecting bismuth. Then all of a sudden, people started calling all these orogenic gold deposits intrusion-related was bismuth. Bismuth is always there. It's always been there. So I better leave it at that. Okay. I think I got them. Oh, here's one more. Just thank you. I think we got all the questions. I think I got them all. But email me with other questions, anyone that has some.
So, yeah, thank you, Dr. Goldfarb. Just on behalf of the SEG UCE FIGEMPA student chapter, we sincerely thank you for sharing your expertise with us today. We truly appreciate your time in contributing to our academic formation. And as a token of our gratitude, we would like to present this certificate of appreciation, which reflects our deep respect for your contribution. Yeah, once again, thank you for being with us today,
I have never
and we
been
look
there,
forward
but
to
hopefully I will
staying in
get down
touch
there,
and to welcome you again in the future, and
visit you
hopefully
guys, and
to
see
see
some
you
deposits
also
at
in
some
Ecuador.
time. And if I see any of you at Pro Expo in Peru, or you're at SGA here in Colorado this summer, definitely come say hello. And definitely I'm on email, so stay in touch on email. Okay, take care. Bye.
Yeah, sure. Thank you, Dr. Goldfarb, and see you next time. Thank you, everybody, for your comments and questions. Thank you.